Hello, welcome to another module in this massive open online course on probability and random variables for wireless communication. So in the previous modules, we have been looking at White's and stationary random process and several interesting properties of White's and stationary random process. So we have seen if xt is a random White's and stationary random process. So let us consider xt, which is a WSS, that is your wide sense stationary. If xt is your wide sense stationary random process, then we have seen what happens when xt is transmitted, that is transmission of xt through a linear, or basically through a linear time invariant system. So we have considered what happens when this wide sense stationary random process xt is transmitted through an LTI system or a linear time invariant system. So let us say we have a linear time invariant system that is represented by this impulse response. So h of t is the impulse response of this LTI system. So I have an input x of t, which is the wide sense stationary random process, output y of t. So we are saying this x of t, this random process is wide sense stationary. This is h of t is an LTI system. Also we said that the Fourier transform of h of t is h of f. So we have h of t whose Fourier transform is h of f. This is also known as the frequency response of the LTI system. So this is the frequency response of the LTI system. This is the frequency response of the LTI system, and when this wide sense stationary random process x of t is transmitted or is passed through this LTI system with impulse response h of t, we said that the output random process y of t is also wide sense stationary. The interesting fact is when an input, when an wide sense stationary random process is input to an LTI system, the resulting output is a random process, and more interestingly the resulting output is also a wide sense stationary random process, right. So yt, so this yt over here, this yt is also WSS, that is your wide sense stationary random process. Further, we had a very interesting relation for the power spectral density, that is if the input power spectral density is Sx of f, the output power spectral density of y is Syy of f, then we had Syy of f equals Sxx of f into magnitude h of f square. This is a very interesting result we had shown, which relates the input power spectral density to the output power spectral density. That is, the output power spectral density Syy of f is the input power spectral density Sxx of f times the magnitude hf square, where hf is the frequency response of the system. Further, we had also looked at another interesting aspect, that is we had looked at a special kind of a random process, that is a Gaussian random process, all right. So we have also looked at what is known as a Gaussian random process. And what is a Gaussian random process? That is xt is Gaussian if, that is your random process xt is Gaussian if we look at the joint distribution f of x of t1, x of t2, comma x of the t, that is random variables x t1, x t2, x tn, x1, x2 up to xn, that is this n random variables. If we look at this joint distribution at n time instant, if this PDF is jointly Gaussian, correct? If the joint PDF of the random process xt at time instants t1, t2, tn, that is the joint PDF corresponding to xt1, xt2, xtn, if this is jointly Gaussian for all possible values of n and also at all times t1, t2, tn, that is if this is jointly Gaussian for all n, for all number of time instants n and for all xt1, xt2 or for all time instants t1, t2, then this is a Gaussian. Such a random process x of t is known as a Gaussian. Such a random process x of t is known as a such a random process x of t whose joint statistics at any set of time instants t1, t2, tn. If you look at the joint probability density function, that is if the joint probability density function at any set of time instants t1, t2, tn is Gaussian, the random process x of t is Gaussian. And in the context of Gaussian random variables, we had also seen a very interesting property, that is a linear transformation or a linear combination of Gaussian random variables leads to another Gaussian random variable. So, we had seen that for a Gaussian random variable, what have we seen? We have seen previously we have seen that a linear transformation of Gaussian RVs, linear transformation of Gaussian R random variables leads to another Gaussian random variable, leads to this. We had seen not in the context of a random process, but we had seen this in the context of random variables, that is a linear transformation of Gaussian random variables leads to another Gaussian random variable. That is, we said that if x1, x2, xn are Gaussian random variables and I consider a1 x1 plus a2 x2 plus so on up till an xn, and I denote this by the random variable x, then this x random variable, this x is Gaussian, this random variable x is Gaussian if x1, x2 so on up to xn are Gaussian. That is, if these random variables x1, x2 up to xn, if these are Gaussian, then the linear combination, that is a1 x1 plus a2 x2 plus so on up to an xn is another Gaussian random variable, that is x. Now, what is the applicability of this? What is the interesting implication of this in the context of random process? It has a very interesting implication in the context of random process. If we consider a linear system, therefore, what is the implication of this in the context of random processes and especially a Gaussian random process? What we have is, let us say we have a linear system again characterized by impulse response h of t, and this is, therefore, the moment we say it has an impulse response, it means that it is, that is, if it characterized by the impulse response, it means it is an LTI system. Then if we input a Gaussian random process, if we input a Gaussian random process to it, and look at the output random process y of t, that is to an LTI system, linear time invariant system, if we input a Gaussian random process, then the output y of t is naturally is a Gaussian random process, because the linear time invariant system is a linear system. So, we are transmitting or we are passing this Gaussian random process, that is linearly transforming this input Gaussian random process. Therefore, the output random process is also Gaussian, which is a linear transformation of the input random process. Therefore, the interesting result is, if you pass a Gaussian random process through an LTI system, the output is Gaussian, another Gaussian wide and stationary random process. So, both wide and stationarity and Gaussianity are preserved when you transmit a Gaussian random process through an LTI system. So, basically this result states, if xt is Gaussian, and passed through an LTI system, LTI system is basically one which linearly transforms. LTI system is nothing but a linear transformation. So, this linearly transforms the input, therefore, the output y of t, we can say that the output y of t, random process y of t is Gaussian. We had already seen that if the input is wide and stationary, the output is wide and stationary. Now, we are saying if the input is Gaussian, then the output is also Gaussian, because Gaussianity of the random variables or Gaussianity is preserved under linear transformation. Therefore, if the input to an LTI system is a Gaussian random process, then the output to the LTI system is also a Gaussian random process, and this is a very interesting result. And we had also seen another special kind of random process, which is white noise. So, we had seen another special kind of random process, which is a very special kind of a random process, which is white noise. And what is white noise? White noise is a random process xt is white if the autocorrelation, that is it is wide and stationary, and the autocorrelation expected value of xt plus xt tau, remember this is your autocorrelation function rxx of tau, this has to be equal to eta by 2 times delta tau. That is, if you look at the autocorrelation function, then the autocorrelation function of white noise is basically an impulse. That is, the autocorrelation of white noise is basically, this is the impulse eta by 2 times delta tau as a function of tau, and this is your autocorrelation rxx tau. And this also means that expected value of xt into xt plus tau is equal to 0 if tau is not equal to 0. That is, if you look at the covariance or the correlation of the random process xt at 2 time instants xt and some non-zero time shift t plus tau, that is expected value of xt times xt plus tau is equal to 0 for any non-zero shift tau, that is these two xt and xt plus tau are uncorrelated. And also, if we look at the power spectral density of this white noise, it has a very interesting property, that is we have, if you look what is the power spectral density, that is we have the autocorrelation, we take the Fourier transform of this and that gives us the we take the Fourier transform of this, and that gives us the power spectral density, that gives us the power spectral density, and that gives us the power spectral density. And now we have for a white noise the Fourier, the autocorrelation is the impulse, therefore, the power spectral density is simply eta by 2 minus f, or minus infinity for all, minus infinity less than f less than infinity. And we had said, we had derived this as follows: for a simple impulse, the power spectral density is uniform 1 over the entire frequency band. Therefore, for eta by 2 times delta tau, the power spectral density is simply eta by 2 over the entire frequency band. So, if I look at this power spectral density, it has a very interesting property. This power spectral density looks simply, it looks, how does it look? It looks simply like this. It is flat over the entire frequency band, that is this is your frequency band, this is your PSD, which has uniform power over all, this has uniform power over all frequencies, that is its uniform power over all frequencies, which is similar to white light, which has basically all the components, or uniform power over all the components of the frequency spectrum. Therefore, this is known as white noise, which has a white power spectral density. This is the characteristic feature of white noise. So, this is the characteristic feature of white noise. It has a white power spectral density, which is similar to white light, or it has a white spectrum. Therefore, such a noise xt is known as it is a white random process, which is also frequently associated with noise. Therefore, it is known as white noise. Now, xt additionally something very interesting which occurs very frequently in communication system. If xt is both Gaussian and white, we said this is your white Gaussian noise, which is very important in the context of a communication system. That is, if the random process xt is both white and Gaussian, then we say this is white Gaussian noise, which is frequently the assumption that is used at the receiver in any communication system, in a digital communication system, in also typically in an analog communication system and a wireless communication system. We use the assumption of additive white Gaussian noise, and that is what has been explained in a previous example. That is, the noise is additive, it adds to the signal, and it is white Gaussian noise, white Gaussian in nature. Such noise is known as additive white Gaussian noise, and the channel which has this additive white Gaussian noise feature is known as an EWGN channel, which is frequently employed to model a digital communication system or a wireline communication system. That is what we had seen in the previous module. Let us now look at another interesting example. Let us now look at an interesting example relating to the processing at the receiver. Let us observe what happens when we process the white noise at the receiver, or at the receiver we process or we pass a white noise through a filter. We filter this white noise at the receiver, or in other words, this can also be said as, when filter the signal plus noise, what happens to the noise at the output of this filter. So, let us look at a typical example from a communication. So, let us as usual look at our typical example in the context of a communication systems. That is, what happens when we process white noise, or let us say what happens when we filter, let us say when we pass it through. So, when we filter this white noise, or when we what happens when we process noise. So, we have, let us consider a white Gaussian noise which is passed through a filter, or white Gaussian noise xt pass through a filter, let us say a low pass filter, pass through a low pass filter. Let us say we pass this noise process through a low pass filter. Let us consider a simple low pass filter. Let us consider this RC low pass filter, your filter which is your typical RC low pass filter. So, the input to this low pass filter is your random process xt, the output is your random process yt. So, we are saying, let us consider what happens to a noise process at the receiver in a communication system. When you pass it through a filter, we are considering an RC low pass filter. We are assuming that this noise process xt, this is the noise process which is xt, which is a white Gaussian random process, right. This is a white Gaussian random process. Therefore, we are also assuming that this is basically wide sense stationary, xt is wide sense stationary. Further, this is white. So, let us, so we are given that the power spectral density of Rxx tau is eta by 2 delta tau, that is the power spectral density of this white noise, which naturally means that the power spectral density Sxx of f is, as we had just seen before, eta by 2 over the entire frequency, it is eta by 2 over the entire frequency band, correct. So, Sx, the power spectral density is eta by 2. Further, let us also assume that this noise is 0 mean. So, we are assuming white Gaussian noise, let us also assume that this noise is 0 mean Gaussian, that implies expected value of x of t is equal to mu of x, which is equal to, that is we are assuming 0 mean Gaussian noise, which means x t is not only Gaussian, but it is 0 mean, that is expected value of x of t, which is mu of x is 0 at every time instant t. Now, what we want to find in this system, so what we are passing this, so this x t is white Gaussian noise, 0 mean white Gaussian noise with power spectral density eta by 2, which we are passing through this RC filter, and this yt is the output. What we want to find is, we want to find the probability density function fyt of y. So, we want to find the probability density function, the PDF of yt at the output, that is noise output of your RC low pass, of your RC, the PDF at the PDF of the noise output of your RC low pass. What is the PDF yt of yt, that is yt, which is the output of this RC low pass filter. Okay, what is the PDF at the output of this process? That is, in the communication system we employ processing. So, let us say we are processing it by the signal by passing it through a low pass filter, and what happens to the noise at the output? What is the noise? That is, the input is white Gaussian, 0 mean white Gaussian noise. What is the distribution of the noise at the output? Okay. So, first thing we have seen, we can see is that basically that RC, this low pass filter, this is a linear system, right. This is a linear time invariant system. So, the first thing is basically this is your, this is a filter, which means this is an LC circuit. So, RC circuit, so RC, so your RC circuit, so your RC filter, so your RC filter is basically is a classic example of an LTI system. Now therefore, as we had seen earlier in this module, since we are taking xt which is Gaussian and passing it through an LTI system, so xt is Gaussian which is passed through an LTI system, which means that the output random process y of t is also the output random process y of t is also Gaussian. The input to the RC filter is a Gaussian random process and it is an LTI system, it is a linear time invariant system, it is after all a filter. Therefore, the output random process y of t is also basically it is also a Gaussian, it is also y of t is also a Gaussian random process. Okay. Alright, so that part is settled. Now let us find the power of this output random process. So let us first find the transfer function for this system. Now most of you must be familiar with phasor analysis. So if I look at the impedance, the complex impedance of this capacitor, the complex impedance is 1 over j omega c as a function of the circular frequency omega. Therefore, y of omega equals the output frequency response is the input frequency response times 1 over j omega c divided by r plus 1 over j omega c, which I can therefore write as x of omega times 1 divided by 1 plus j omega c. Now therefore, if I look at the transfer function is nothing but the ratio of the output frequency response y of omega to the input frequency response x of omega. What is this? This is h of omega, which is your h of omega, which is your transfer function. This is equal to 1 over 1 plus j omega RC, this is your transfer function. Now if I substitute omega equals 2 pi f, that is the circular frequency omega equals 2 pi f, then I have the transfer function in terms of f equals 1 over 1 plus j 2 pi f RC. This is the transfer function in terms of f of this circuit, that is the transfer function h of f equals 1 over 1 plus j 2 pi f R C as a function of the frequency f. R is the resistance of the circuit, R is the resistance, C is the capacitance. Okay. And now therefore, if we look at the output power spectral density, we have for this LTI system the output process y of t is wide sense stationary and the output power spectral density is Sxx of f, input power spectral density, times magnitude of h of f square. Now Sxx of f is eta by 2, that is white noise, remember white noise of power spectral density eta by 2 into 1 magnitude h f square, which is 1 over 1 plus 4 pi square f square r square c square, and therefore I have my expression for the power spectral density. What is Syy of f? This is the power spectral density of your output random process y of t. So we have inferred two things. One is the input random process xt is Gaussian, therefore the output random process y of t is also Gaussian. Further, the power spectral density of the output Gaussian random process is Syy of f, which is equal to eta over 2 times 1 over 1 plus 4 pi square f square r square c square. Now we can find the power of this output random process, that is simply the integral of the probability density function of the power spectral density from minus infinity to infinity. Therefore, the power expected, remember there are several concepts that are coming together in this example, that is the integral of minus infinity to infinity Syy of f times df. which is equal to, what is this equal to? This is equal to minus infinity to infinity, eta by 2 is a constant. So, that is comes outside 1 plus f square 4 pi square r square c square times df, that is integral of power spectral density over the limits minus infinity to infinity, which I can write as eta by 2 1 over 4 pi square r square c square integral minus infinity to infinity df by f square plus 1 over 4 pi square r square c square. Okay. So, I have simplified this integral, and this integral can be evaluated, in closed form. In fact, it is eta over 2 1 over 4 pi square r square c square times 1 over square root of this, that is 1 over square root of this, that is 2 pi r c times tan inverse f divided by 1 over 2 pi r c between the limits minus infinity to infinity, and now if I simplify this further, what we have is eta over 2 1 over 4 pi square r square c square times 2 pi r c is basically 1 over 2 pi r c, and evaluating tan inverse of infinity is pi by 2, tan inverse of minus infinity is minus pi by 2. So, I have pi by 2 minus pi by 2, that is pi. So, that is equal to pi, which is equal to eta by 4 r c, and remember what is this quantity? This is your expected y square t or expected magnitude of, this is your expected magnitude of y square t, or this is basically the power in the Gaussian random process, that is expected value of magnitude y square t. This is also RYY of RYY at tau is equal to 0. This is the integral of the power spectral density of y over the entire frequency range. This is also RYY, that is the autocorrelation function of y evaluated at 0, that is autocorrelation function of y evaluated at 0. So, we have found the power in the Gaussian random output process y. Now, also we are given that x t is 0 mean. Now, that implies expected value of x of t equals mu of x, which is equal to 0, which means now we also know that mu of y from our again transmission of random process through LTI system is minus infinity to infinity h of t dt times mu of x, that is the output mean, equals integral of the impulse response over the entire time times mu of x, but mu of x equal to 0, which means the output mean is also equal to 0, that is mu y, the input mean is 0, the mean of the input random process x of t is 0, therefore, the mean of the output random process y of t is also 0, which means the power of the random process is the same as the variance. What is the, so the mean is 0, which means expected, the variance is expected y t minus mu y whole square, which is equal to, again mu y is 0, this is equal to 0. So, this reduces to expected y square of t, which is equal to basically your what is that equal to? So, this is basically equal to eta, we have already derived this, this is equal to eta by 4 RC, and what is this? This is basically the variance of your Gaussian random variable. So, we have y of t is a Gaussian random process. So, at each time instant t, y of t is basically Gaussian. Remember, the joint statistics are Gaussian. So, at each time instant it is Gaussian. The mean mu of y equals 0. The variance, if you were to call it sigma y square, that is equal to eta by 4 R C. Yeah. And therefore, the probability density function, remember the joint probability density function at any combination of times is Gaussian. Therefore, if you take at any particular time t, the probability density function of y of t is Gaussian. Therefore, the probability density function f y of t, now I can write, I know it is Gaussian, I know it has mean mu, I know it has variance sigma y square. The probability density function f y t of y equals 1 over square root of 2 pi sigma y square e raised to minus y minus mu y whole square divided by 2 sigma y square, which is equal to, now if I substitute the values for these parameters, that is equal to 1 over 2 pi. Now, sigma y square is 1 over or eta over 4 R C times e to the power of minus, now mu y is 0. So, e to the power of minus y square by 2 sigma y square, which is again eta by 4 R C, which is equal to, of course, I have to have a square root over here, 1 over square root of 2 pi sigma y square. So, now if I substitute this, what I have is basically I have square root of 2 R C over pi eta times e raised to minus 2 R C y square divided by eta. And what is this? This is the PDF of your output random process. So, this is the PDF of y t at time instant t, that is the PDF. What is the PDF? F of y t, PDF of the random variable y of t at time instant t. All right. So, this illustrates an interesting, a very interesting example in the context of communication systems, that is what happens at the receiver when you process, that is you go through different stages of processing of the signal. At each stage you have both outputs, you have the signal output and you have the noise output. So, at each processing stage, how is the noise output modified? So, what we have seen is a simple example, that is when we filter this signal, remember the signal has noise added to it. So, when we pass the signal through the processor or through this filter, the noise is also passing through the filter, and what we have derived today is basically something very interesting. If you have white Gaussian noise of power spectral density eta by 2 at the input of this low pass RC filter, then the output is also white and stationary Gaussian noise. It is no longer white because you are passing it through a filter, right. And in fact, we have also derived the expression for the power spectral density. It is no longer white, the power spectral density of this noise at the output of this RC filter, the power of this Gaussian noise at the output of this RC filter is eta divided by 4 RC, and we also derived the probability density function, the Gaussian probability density function at time instant t for this output Gaussian noise. All right. So, this comprehensively explains or illustrates several aspects of white and stationary random process, that is white and stationary random process, a white random process, a Gaussian random process, a white Gaussian zero mean random process, and what happens when you transmit this through an LTI system, how does the LTI system affect this noise at the output. And this such processing or such knowledge or such these results play a very important role in the analysis of digital communication systems and also wireless communication systems in particular. So, we will end this module here. Thank you very much.